Okay, so it looks like, let's see. Okay, so it looks like we're live on YouTube. So what I'm going to do now is share my screen and go to the PowerPoint here. Okay, so y'all, whoops, wait a minute. Okay, I just got a feedback from YouTube, which I had to take care of. Okay, so let me go to the PowerPoint here. Okay, please let me know if you can see my screen.
I can. I'm good.
Okay, good. All right. If you can, then I'm sure the rest of your classmates can. All right. So this was the last thing we discussed last time. We talked about the difference between the empirical formula and the molecular formula. So just to remind you quickly, the molecular formula gives you the number of atoms of each element present per molecule, while the empirical formula gives you the simplest ratio of the different elements present in the substance. And I remember telling you that there is a whole number relationship between the molecular formula and the empirical formula. To get from the empirical formula to the molecular formula, what you'll have to do is multiply each of the subscripts by a certain integer. And when you do that, you'll end up with the molecular formula. And some of the problems that we're going to look at involves determining what that integer is. In some textbooks, they call it the integral factor, right? So you'd have to multiply the empirical formula by the integral factor in order to get the molecular formula. So we're going to go through a couple of examples to begin today's class so that you get a feel for the type of problems that you could encounter in your future quizzes and exams. So here's the first example. You have a compound that is comprised of 3 elements: carbon, hydrogen, and oxygen, all right? And they gave you the percentage of each element present in the compound. So you see you have 40.01% carbon, 6.72% hydrogen, and 53.2% oxygen. And the question is asking for you to calculate the empirical formula, all right? So this is how you'd go about doing it. So let me get out of this here and get to this. So as you can see, I've already set up a table where I have carbon, you have 3 columns, 1 for carbon, 1 for hydrogen, and 1 for oxygen, all right? So the first step in this process, because the question actually gave you the percentages of each element. So the first step in this process is that you simply assume that you have 100 grams of the compound that you're working with. And the reason why we assume that is that if we assume 100 grams of the compound, then that means that the masses of the elements would be the percentages expressed in grams. So in other words, for 100 grams of the compound, you're going to have 40, as you can see, I've written here already, 40.01 grams of carbon, 6.72 grams of hydrogen, 53.27 of oxygen, all right? So those are the masses of each element present per 100 grams of the compound. Now you could use any other mass total for the compound, but 100 grams is more convenient because you don't have to do any conversion. You just simply express the percentages as the masses, and that will work fine. Okay, so that's the first step. Now the next step is that you need to determine the moles of each element. And this is something that by now we all should know how to do. To get the moles, we simply divide the mass in grams by the respective molar masses of each of the elements. So in the case of carbon, you divide 40.01 grams by, or you could multiply it by 1 mole over the molar mass of carbon, which is 12.01 grams, all right, per mole, all right? And we do the same thing for the other elements, 6.72 grams for hydrogen, multiplied by 1 mole divided by 1.008 grams. And in the case of oxygen, 53.27 grams. We multiply that by 1 mole over 16.00 grams. Give me a minute. Let me turn on this fan here so I can get some more air circulating. 1 minute. Okay.
Did I miss anything? I arrived like a little late.
Oh, not a whole lot. We just went back over some stuff.
Okay, sorry about that. Am I missing a conversation I should be a part of, or?
No, I was just asking if I missed anything important.
Oh, okay. You mean for today?
Yeah.
Oh, we just started, so you haven't missed much. All right, so if you have any questions, of course, feel free to chime in and let me know so that you can catch up. Okay, so at this stage, as I said before, we're calculating the moles, right? So basically, I need to take out my trusty cheat calculator here. And by the way, I would strongly advise that you actually do the calculations along with me, because I could make a mistake and you could catch my mistake. That would be very helpful for me so that I can correct any errors that I make. All right. So I would suggest that you take out your calculator and do the calculations along with me, which is what I'm going to do right now. So I'm going to start off with 40.01. Whoops. I need to clear that first. 40.01 divided by 12.01. And according to my calculations, this works out to be, and I have to round this off to 4 sig figs. So this works out to be 3.331. So I'm going to write 3.331 moles. And then I'm going to do the same thing for hydrogen, which would be 6.72 divided by 1.008. And according to my calculations, this works out to be equal to 6.67. So let me put 6.67 moles. Oops. Okay, what's going on here? Moles. And then finally, in the case of oxygen, 53.27 divided by 16. And according to my calculations, round off to 4 sig figs. So this will be equal to 3.329 moles. All right. So that's basically what we do at this stage. All right. So now that we have the moles of the different elements present, the next step is to find the simplest ratio, because that's what the empirical formula is all about. And to get the simplest ratio, what we have to do is look at the values that we get at this stage here and divide it right through by the lowest one, which by my examination would be the 3.329. So that means you have to divide each of these numbers by 3.329 moles. So here you're going to have 3.331 moles divided by 3.329 moles. And I'll do the same thing here, 6.67, whoops. Let me get the eraser. And then go back to my pen function. Okay, so 6.67 moles divided by 3.329 moles. And then finally, this divided by itself will give you 1. So I'm just going to put 1 right here. All right. So let me again calculate 3.331 divided by 3.329. And according to my calculations, this works out to be 1. Let me see here, 4 sig figs. So that would be 1.001. Of course, the mole units will cancel out here and here, so there'll be no units left here. In this case, 6.67 divided by 3.329. And according to my calculations, rounded off to 3 sig figs, that would be 2.00. 2.00. And again, as I said before, this is 1. So these numbers that we end up with at this point should be integers, right? So all we have to do is approximate this to 1, approximate this to 2, and this will be 1. So therefore, the empirical formula, let me just squeeze it in right here, based on what we have just done, would be equal to C1H2O1, or simply CH2O, all right? And of course, the numbers that we end up here as subscripts would be the corresponding numbers that we have determined here, here, and here. And that's basically how this problem is solved, all right? Any questions about this? Any questions? Any questions? Okay, if there are no questions about this one, we're going to do another example, because what you'll find is that some problems of this type would not work out neatly as we have determined here. All right, so let me go back to the PowerPoint and move on to this example. And this question says, phenol, a general disinfectant. Let me make this bigger. Phenol, a general disinfectant, has the composition of 76.57% carbon, 6.43% hydrogen, and 17.00% oxygen by mass. And again, you're asked to determine its empirical formula. So the approach would be the same actually as what we did before. So let me get out of this, go back to my, go back to this. I'm just going to get rid of all of this. And I'm going to set up a new table. Again, the elements are the same. So it's going to be carbon, hydrogen, and oxygen. And just as before, we're going to assume that the percentages will be the same as the masses. In other words, we're going to assume 100 grams of the compound. So according to the question, so I'm going to start off with the mass row right here. So according to the question, we have 76.57% of carbon. So we're just going to write down here, 76.57 grams of carbon. And then in the case of hydrogen, 6.43 grams of hydrogen. And then in the case of oxygen, 17.00 grams, all right? So basically the same setup as before. We simply express the percentages as masses in grams, all right? Okay, so the next step is that we determine the moles, just like we did before. So if you recall, in the case of carbon, we will multiply the mass in grams by 1 mole over 12.01 grams. In the case of hydrogen, 6.43 grams multiplied by 1 mole over 1.008 grams. And finally, in the case of oxygen, 17.00 grams multiplied by 1 mole over the molar mass, which is 16.00 grams. All right. So again, we have to do some computation here with our calculators. So let's do that together. So in the case of carbon, it's 76.57 divided by 12.01. And according to my calculation, this works out to be, I have to round off to 4 sig figs. So this would be 6.376. So here, I'm going to put 6.376 moles. And then in the case of hydrogen, 6.43 divided by 1.008. According to my calculations, this works out to be equal to 6.38 moles. So equals to 6.38 moles. And then in the case of oxygen, 17 divided by 16. And according to my calculations, rounded off to 4 sig figs would be 1.063. So this would work out to be equal to 1.063 moles, all right? So we got our moles, and if you recall, the next step would be to divide right through by the lowest mole value that we just calculated. Based on my calculation, that would be the oxygen here. So you multiply everything in this row by 1.063 moles. So in the case of carbon, that would be 6.376 moles divided by 1.063 moles. In the case of hydrogen, would be 6.38 moles divided by 1.063 moles. And then this would be 1, of course, because when you divide it by itself, you're going to get 1. So Again, we have to go to our calculators to calculate the other two. So for carbon is 6.376 divided by 1.063. So according to my calculations, this works out to be equal to 5.998. And then I do the same thing for hydrogen, 6.38 divided by 1.063. And according to my calculation, this works out to be equal to, whoops, what's going on here? 6.366, so 6.00. And then of course, this is 1, so we don't need to do anything here. So again, as I said before in the previous example, when you get to this stage, these numbers actually should be integers, whole numbers. As you can see, this is very close to 6, so we can just simply round this off to 6. So this would be approximately equal to 6. This would be rounded off to 6 as well. So therefore, the empirical formula, hold on, let me squeeze it over here. The empirical formula will be equal to C6H6O, and that will be the empirical formula for phenol. All right, so it's very similar to what we did in the previous example. All right. Okay, are there any questions about this one? Any questions? Any questions?
Yeah, this one.
Or is there a question? Okay, so let's move on now to a third example. Let me go back to the PowerPoint here. So the second example on this page, actually. So in this case, they're dealing with a compound known as diethylene glycol, oftentimes used as an antifreeze. And for those of you who have to do Chem 2, you're going to learn how antifreeze works in terms of elevating the boiling point of water of the solution and lowering the freezing point. And therefore, as a result, when you put it in an engine, you know, like in your radiator in a motor vehicle, you know, during the winter months, if you live in a cold climate, the engine won't freeze up as easily. And in warmer climates, the engine won't steam up and heat up easily because of the role of the antifreeze. So that's just something for you guys to look forward to in general chemistry too. For now, what we'll be concerned about is calculating the empirical formula based on the data that is given. And again, the principle is the same as in the previous two examples, right? So let me go back to this. Let me clear this. Okay, and it's the same three elements again: carbon, hydrogen, and oxygen. Okay, so the first step, of course, would be their masses. And based on the question, the percentages, again, like we did before, will be expressed as their masses. So here you're gonna have 45.27 grams for carbon. For hydrogen, 9.50 grams. And for oxygen, 45.23 grams, all right? So the next step is to determine the moles, just like we did before at this stage. 45.27 grams multiplied by 1 mole over 12.01 grams. In the case of hydrogen, 9.50 grams multiplied by 1 mole over 1.008 grams. And then in the case of oxygen, 45.23 grams multiplied by 1 mole over 16.00 grams. And again, we use our calculators to crunch these numbers, starting with the carbon, 45.27 divided by 12.001. Okay, so according to my calculation, this works out to be round off to 466, so that would be 3.769 moles. And then in the case of hydrogen, we divide 9.50 by 1.008. And according to my calculations, this works out to be, I have to round out to 3 sig figs. So this would be 9.42 moles. And then finally, in the case of oxygen, 45.23 divided by 16. According to my calculations, this works out to be 4 sig figs, so 2.826 moles. All right. Okay. So once we get the moles, the next step, if you recall, as we did in the previous two examples, is that we look at these three numbers here, and we try to determine which one is the lowest one in value and divide right through by that value, which would be, again, the moles of oxygen. In this case, would be 2.82 moles. So we're going to divide by right through by 2.826 moles. So here we're going to have 3.769 moles divided by 2.826 moles. Here we're going to have 9.42 moles divided by 2.826 moles. And here again, we're going to have 1 because we divided by itself. So again, we're going to go to our calculators. For carbon, I'm going to divide 3.7 69 divided by 2.826. And according to my calculations, I got 1. Round off to 4 sig figs, 1.334 as your answer. The mole units will cancel out here and here. Divide 9.42 by 2.826. And according to my calculations, when rounded off to 3 sig figs, that would be 3.33 moles. And again, this would still be 1. Now you'll notice that in this particular case, at this stage, you have these numbers here, which are not anywhere close to an integer, right? So in this particular situation, if you do a problem and you get a situation like this, the question you have to ask yourself at this point is, what do I multiply these numbers by to convert them to integers, right? And you'll notice that in both cases, you have a recurring 3 after the decimal point, right? So if you have a recurring 3 after the decimal point, if you want to convert each of these into integers, you have to multiply right through by 3, right? And let's see what happens here. If you multiply 1.334 by 3, you're going to get 4.002, all right? And you'll see that this is very close to an integer, right? Let's look at the 3.3. 3.33 times 3. What do we get? We get 9.99, which again is very close to an integer. And then finally, when we multiply 3 by 1, we're going to get 3, right? So because these two are close to integers, we can just basically round them off. In this case, round this off to 4, round this off to 10, and therefore the empirical formula becomes C4H10O3. And that's basically how that is done. All right. Okay, any questions? So let me just recap right here, because this is where things are a bit different compared to the other examples. When you get numbers like these, which are very far from an integer, I would say that the numbers that you get should be at least plus or minus 0.1. Or I would say plus or minus 0.1 or plus or minus 1 from an integer. And that is certainly not the case for these numbers here. 1.334 is not close to the nearest integer, which is 1. And the same is true for 3.33. So when you get to a situation like this, what you should do is figure out what you should multiply these numbers by in order to get a result which is close to an integer, if not equal to an integer. And as I said before, I identified that there's a recurring 3 after the decimal point. So that kind of clued me in to the fact that I should multiply these values by 3. And as a result, we end up with these numbers here, right? So there are certain things you should look out for when you get to this stage, right? If you have a recurring 3 after the decimal point, then you multiply right through by 3. If you have a recurring, let me just find a space somewhere to write what I'm saying. So if you have this, if you have a recurring 3 after the decimal point, you multiply by 3. If you have a recurring 6 after the decimal point, you multiply by 3. If you have a 0.5 after the decimal point, you multiply by 2. If you have a 0.25 after the decimal point, you multiply by 4. If you have if you have a 0.75 after the decimal point, you multiply by 4. If you have a recurring 1 after the decimal point, you multiply by 9. Those are the ones I can recall from the top of my head. In other cases, you have to do trial and error, right? So you try a number, like 7, or like 9. Well, I talked about 9 already, but try some other number that you multiply by so that when you get to, as I said before, this stage, when you get to this stage, you multiply these numbers by that number that you're trying and then see if it works out to be an integer. And then those integers would be the subscripts in the empirical formula. Okay, so are there any questions about this particular example?
Not I.
All right, so let's move on now to a discussion of something I'm quite sure you have not met in, unless your teacher was very excited to introduce this to you, but I've never introduced this to my introductory class, so I would imagine this would be the first time you'll be meeting this topic of elemental analysis. Okay, so elemental analysis is basically a procedure for determining the mass of elements present in a particular compound, all right? This approach is normally used for simple organic molecules which contain carbon, hydrogen, and maybe oxygen, and maybe some other elements, right? So basically the way this works is that the compound, you weigh the compound first, and then you burn it in oxygen. Now, you should have learned in your introductory chemistry class that whenever you burn any compound in oxygen, any organic compound in oxygen, the products will be carbon, hydrogen, carbon dioxide and water. Those will be the products. In fact, let me go back to my writing pad here. And let me clean this up. So as I was saying, any compound that contains carbon, hydrogen, and oxygen, when you burn it in air, it reacts with oxygen to form carbon dioxide and water, all right? And the same is true if you burn a compound which contains carbon and hydrogen only, all right? Plus O2, again, the products will be CO2 and H2O, all right? So any compound that contains carbon and hydrogen only, they're called hydrocarbons, all right? So hydrocarbons, when burnt in air, will give you the products carbon dioxide and water, and also any organic molecule that contains carbon, hydrogen, and oxygen, all right? Will give you, again, carbon dioxide and water. All right, so this is something that you need to understand in order for you to understand elemental analysis. So going back to the PowerPoint slide. Okay, so as I was saying before I left the slide, after burning your compound in oxygen, the products will be carbon dioxide and water. Now, the key thing is this. If you could find some method of measuring or weighing the mass of carbon dioxide and water produced, then you can use those masses to determine how much carbon and hydrogen was present in the original compound, all right? So going back to the writing pad here, if you can somehow determine the mass of the carbon dioxide here, you can get the mass of carbon. From this, you can get the mass of carbon. Mass of carbon. And if you can determine the mass of water here, you can use this to determine the mass of hydrogen. And if you can determine the mass of carbon here and the mass of hydrogen here, those will be the same as the mass of carbon here and the mass of hydrogen here, all right? And then if we have, so this is mass of carbon and mass of hydrogen. Oops, right? And once we determine these masses, what's going on here? Once we determine these masses, then we can determine the empirical formula for the compound, all right? And we're going to see an example of this shortly. But before we do that, I just want to show you this diagram right here, which is a schematic representation of the experiment for the analysis of, organic compounds of the type I just described. So you'll notice that we have a series of compartments here linked to each other by tubes, all right? In the first compartment, that basically plays the role of the furnace where you're going to burn your sample. So here's your sample in a dish and it's subjected to heat and oxygen. So basically the combustion reaction is going to take place here. And the products of the reaction would be carbon dioxide and water, right? Which would be in a gaseous state. So once we burn all of the sample here, the CO2 and H2O will make its way through this tube into this compartment. Now, this compartment contains a substance, magnesium perchlorate, which will absorb the water that is present or that is coming from the furnace, right? So basically, we have to ensure that we have enough magnesium perchlorate in order to absorb all the water that is produced. And also, we have to weigh the magnesium perchlorate before we start the experiment. So when this absorbs the water that is produced from the furnace, there'll be an increase in mass, right? Because first you have the dry magnesium perchlorate, it absorbs water, the mass will increase, and therefore you can weigh the difference between, or calculate the difference between the two masses initially and after the absorption of water, and that would give you the mass of the water, all right? And then, as I said before, if enough magnesium perchlorate is here to absorb the water, then the only thing that should be emanating from this compartment would be carbon dioxide, and that would be led into here, where you're going to have another substance which will absorb the carbon dioxide, which in this case would be sodium hydroxide. And again, you're going to determine the mass of the carbon dioxide by the difference in masses before and after the reaction, and therefore that would give you the mass of the carbon dioxide that you're going to need in order to calculate the empirical formula for the compound. All right, so that's basically an overview of how we do this sort of analysis. Okay, so that leads us now, let me just skip all this because I described it already. That leads us now to this example. So this question says that menthol, that's a compound of interest here, contains carbon, hydrogen, and oxygen. And it says that a 0.1005 gram sample of menthol was combusted, which is basically mean burnt, and it produces 0.289 grams of carbon dioxide and 0.1159 grams of water. So the question is asking, what is the empirical formula for menthol? Okay, so again, I have to go back to my writing pad here, get rid of all of this here. And okay, I don't know where this came from, so let me get rid of that. Okay, I don't know what is going on here. Or maybe I should do this. Okay, I think that takes care of that. Okay, so this will be a very involved process. So I want you to follow what's happening here. And let me just say that, because of the level of complexity, it's very easy to make errors, which could screw up your final answer. So I'm going to try to go through this as carefully and slowly as possible, all right? So the first thing I'm going to do here is start off with the mass of carbon, all right? So to get the mass of carbon, we have to first start off with the mass of carbon dioxide, which is 0.2829 grams of CO2. So the next step would be to convert the mass of carbon dioxide to moles. So of course we have to find the molar mass of CO2, which means that we have to go to the periodic table. We have to add up the molar masses of carbon, which is 12.01, and then for oxygen, which is 16.00 multiplied by 2. So that would give you 44.01 grams of CO2. And up here, you're going to have 1 mole of CO2. all right? So this goes with that. So up to this point, you would have determined the moles of CO2. The next step would be to determine the moles of carbon, 1 mole of CO2 below. And based on the formula where you have a 1 here is in subscript, that means that you're going to have 1 mole of carbon above. And then the next step would be to find the mass of carbon. And that means we have to multiply by the molar mass of carbon. So 1 mole of carbon down here and 12.01 grams of carbon above, all right? So this will go with this will go with this, and then we need to do our number crunching. So 0.289, I'm sorry, 0.2829 divided by 44.01, multiplied by 1 times 12.09. Okay, so according to my calculation, this works out to be equal to 0.0. Okay, I need to round this off to 4 sig figs. So this would be 0.07772 moles. All right, so that would be, I'm sorry, grams. So that would be the grams of carbon. And then I'm going to do the same calculation, the same setup for oxygen, I'm sorry, for hydrogen, mass of hydrogen. And it's going to be a similar process as we did just now. So according to the question, the mass of water would be 0.1159 grams H2O. And we convert that to moles. So you're going to have 1 mole of H2O. And again, we have to go to the periodic table and add up the molar masses of the hydrogen and the oxygen. I've already done that. The answer is 18.02 grams of H2O. And here is where students very often slip up, right? Now, if you recall at this stage here, there's a 1-to-1 mole ratio between the carbon and the carbon dioxide, right? Based on the formula. However, in the case of water, you have 2 hydrogen atoms per molecule. So therefore, what that tells you is that for every 1 mole of H2O, you have 2 moles of hydrogen. And therefore, the way you'd represent this here is that you're going to have 1 mole of H2O down here and 2 moles of hydrogen above, all right? Very important. I can't tell you how many times I've graded work from students and they forget to put 2 here instead of 1. So please make a note of that. The next step is in the final stage here, where we multiply by the molar mass, in this case of hydrogen. So 1 mole of hydrogen will be down here, and 1.008 grams of hydrogen will be above, and work this out. So 0.1159 divided by 18.02 times 2 times 1.008. And according to my calculations, when you round off to 4 sig figs, you're going to get 0.0 4 sig figs. So this will be 0.013 00, because I have 0.01296. So yeah, so this would be the moles, I'm sorry, the grams of hydrogen, all right? So, so far we have the mass of hydrogen and we have the mass of carbon. But remember, the question says that there's a third element, and that is oxygen. So how do we get the mass of the oxygen? So to get the mass of the oxygen, what we have to do is take the total mass of the compound, which according to the question is 0.1005 grams, and we subtract from that the sum of 0.07772 grams plus 0.01300 grams, all right? So I need to take out my calculator and work this out. So what I'm going to do is work out what's within the parentheses first. 0.0772 plus 0.01300. And then I'm going to subtract that from 0.1005. Okay, what did I do wrong here? Let me do this again. 0.0772 plus 0.01300. And then I'm going to subtract from that 0.1005. Okay, so according to my calculations, this works out to be equal to 9.78 times 10 to the minus 3 grams. All right. So now we have the mass of each element present in this compound. We have the mass of oxygen, which we just calculated down here. We have the mass of hydrogen, and we have the mass of carbon. So, believe it or not, we're just halfway to solving the problem because we need these values. And I need more space. Okay, so what am I going to do? What I'm going to do is write down these numbers so I can okay, so what I'm going to do is I'm just going to clear this. And I'm going to start now setting up my table for calculating the empirical formula. How much time do we have left? Okay, we have enough time. At the top of the table, I'm going to have carbon, hydrogen, and oxygen, just like we had before. And this time, what I'm going to do is write down the masses that we just calculated for each of these elements in this row right here. So in the case of carbon, it was 0.07772 grams. In the case of hydrogen, it's 0.01300 grams. In the case of oxygen, it's 9.78 times 10 to the minus 3 grams. And then we do the same thing that we did before. In other words, we calculate the moles at this point. So we're going to take 0.07772 grams and multiply it by 1 mole over 12.01 grams. And then do the same thing for the hydrogen. So multiply that by 1 mole over 1.008 grams. Whoops, 8 grams. And then finally, in the case of oxygen, times 10 to the minus 3, multiply that by 1 mole over 16.00 grams. And then we do our calculation of the moles. So according to my calculator, 0.07772 divided by 12.01. And the answer I got is 6. Round off to 4 sig figs. So I would get 6.741 moles. Do the same thing for the hydrogen, which is 0.013 divided by 1.008. And according to my calculations, when rounded off to 4 sig figs, that would be 0.012. Okay, 0.0. This looks like 0.1290 moles, all right? And then in the case of oxygen, 9.78 times 10 to the minus 3 divided by 16. And according to my calculation, I get rounded off to 3 sig fig, 6.11 times 10 to the minus 4. Yes, minus 4. 10 to the minus 4 moles, all right? Okay, so now that we have the moles at this point, we look at these numbers, decide which one is lowest in value by inspection, and I see Okay, something is looking wrong here. This can't be right. I just realized something. Let me do this, the first one again. 0.07772 divided by 12.01. Okay, I forgot to write multiply by 10 to the minus 3 here. Very important. Very important. I'm glad I caught myself on that one. That's why I need you guys to calculate along with me so that, you know, if I slip up like I just did, you should be able to catch me up on that. Okay, so as I was saying, we need to determine which of these would be the lowest in value, which would be this one right here. So we divide everything in this row by 6.11 times 10 to the minus 4 moles, right? So in this case, we're going to divide 6.741 times 10 to the minus 3 moles by 6.11 times 10 to the minus 4 moles. Here we're going to divide 0.01290 moles divided by 6.11 times 10 to the minus 4 moles. And this would, of course, would be equal to 1 when divided by itself. So I'm going to divide now. Oh, shoot, I realized I made another mistake here. Hold on, let me check and make sure. 0.07772 divided by 12.01. Okay, I made another serious error. This here should be 6.47. Why did this happen? 6.4. This should be 6.47 here. I don't know why it's not writing. Oh my goodness, I hate when this crap happens. What? Okay, I must apologize for this. I don't know why this technical issue. Okay, I don't know where that line came from. It's not allowing me to write down what I need to write down here. This should be 4.7, and this should be 4.7 as well. All right, so I'm sorry about this, but make a note of this. Wherever you see 6.741, it should be 6.471, all right? For some reason, I'm not sure why, excuse me, the software is not allowing me to write above the line or below the line. I don't know what's going on here.
I do see a button there in the
Where?
middle that has an X on it. Maybe
A button in the middle.
right perpendicular down from there. Or
Oh, here.
yeah, there's one right below it, and it's got an X on it that you might be able to get rid of it with.
Okay, I think I just did. Let me see now.
Well, it moved.
Yeah.
Oh,
Yep.
Still not. Hold
Yeah,
on.
there.
Oh, wait a minute. There's several of these right here. I just see them. Let me see here. Oh, let me do that.
Yeah, that one.
Oh, okay.
Cool.
Okay, now it's writing. Okay, thank you. Thank you very much. Okay, so I was saying this should be 471. This here should be 471, right? Okay, so what I'm going to do now is divide 6.471 times 10 to the minus 3 by 6.11 times 10 to the minus 4. And according to my calculations, this works out to be equal to 10.59. I have a sneaking suspicion this is not correct, but I'm just going to go along with it for the time being. In the case of hydrogen, it's 0.01290 divided by 6.11 times 10 to the minus 4. And according to my calculation, this gives 21.11. I have a sneaking suspicion something is wrong here, and I'm not sure what it is. Anyway, so basically, we can round this off to 11. We can round this off to 21. This will be 1, so therefore the empirical formula is going to be C11, H21, O1, all right? I have a sneaking suspicion that this is not correct, so I'm going to look over this particular problem, and I think what I'll do is post a video of that solution, all right? But basically the process that you're gonna go through is what I just outlined, all right? So as you can see, there are 2 parts to this process. The first part is determining the masses of the elements from the combustion data, right? Once you get the masses of the elements in the compound, then you set it up like what you see here on the screen, and you go ahead and do your process just as we did in the other examples, all right? Okay, are there any questions concerning this example?
I'm fine. I don't have any questions. Anybody else?
Yeah, anybody, any questions, issues, any area of clarification needed? Okay, so let me go on to, okay, so that's basically it as far as combustion analysis is concerned. So what we're going to talk about next is stoichiometry, and this is going to be the last topic for this class, all right? So stoichiometry, again, this is something that you should have met in your introductory or high school chemistry. Basically, stoichiometry is that area of chemistry which deals with quantitative relationships between substances involved in a chemical reaction, all right? And this is a very fundamental concept that you need to grasp before you can do a lot of other things later on, right? Because it's very fundamental. It's actually a result of the conservation of mass law that we talked about earlier, all right? So of course, in stoichiometry, the first thing you have to start off with is a balanced equation. And we know that an equation will have reactants represented on the left side, products on the right side, and you have an arrow pointing from the reactants to the products, all right? So we need to basically be able to write down a balanced equation for any reaction that you're given. And we all know that a balanced equation is a shorthand way of expressing what is happening in a chemical reaction. There are some symbols involved. I mentioned before that the reactants are on the left and the products are on the right. And in a balanced equation, we separate them using plus signs. And then, of course, we use arrows to point to where the products are formed. And what else? Some other notations that you'll encounter when you're writing an equation or when you see an equation. You'll see these symbols, right, in parentheses, right beside the formulas, indicating the states, right? Gas, liquid, solid, and the aqueous state, which means that the substance is dissolved in water. And then there's some other notations you might see, such as this small triangle here, which represents heat. In some cases, you might see some other additional information. So for example, you might see the actual temperature given, you might see pressure given, and other information just to give you the conditions for the reactions, all right? Okay, so let's consider a simple example, an equation for the formation of water from hydrogen and oxygen, all right? So the first thing you need to do is write down the symbols of the reactants and products. So the reactants are on the left, the hydrogen and oxygen, and the product, one product in this case, water, H2O, right? So that's the first step. The next step is that you must recognize, as I said before, that the conservation of mass law must be obeyed, which means that the equation must be balanced. In other words, you have to ensure that the number of atoms of each element on either side of the equation would be the same, right? So we have to make some modifications to this equation in order to ensure that is the case, right? So if you look at each equation, or if you look at each side, I should say, you'll see that whereas you have the same number of hydrogen atoms here and here on both sides, the number of oxygen atoms are different. You have 2 oxygen atoms here, you have 1 here, right? So the question now becomes, how do we make sure that the number of oxygen atoms here and here are the same, all right? So what we have to do is add whole units as coefficients, right? Before the formula for the particular element or compound substance that needs to be balanced in order to make sure that we achieve the balance of number of atoms of the same element will be the same on both sides. Now, I want to show you this diagram here because this diagram shows you 2 incorrect ways of balancing equations. And here you have the correct way of balancing it. So what you cannot do when balancing an equation is simply add an element to one side in order to achieve the balance, right? Cannot do that. You're basically creating an element out of thin air in order to achieve this, right? So you cannot just simply add an element to one side in order to achieve the balance. Another thing you cannot do is add any subscripts or change the subscripts for any formulas, right? Again, what you're doing is creating a new substance out of thin air. So therefore, like in this case, you cannot just simply add a 2 here to get this, all right? So the right way of making the balance occur is that you make changes to the coefficients, which would be the integers that you place in front of the formulas. So in this case, in order to balance the equation, or more, whoops, running out of juice. Let me make sure I plug this in before it shuts off. Where is the plug? Here it is. Okay, so as I was saying, in this particular case, to balance the oxygens, you place a coefficient of 2 here, right? But by placing a coefficient of 2 here, we are now having an imbalance of the hydrogens. So therefore, we have 4 hydrogens here. So we're going to need 4 on this side, and that's why we put the 2 here. And now the equation is balanced, right? So basically, what you need to do is make changes to the coefficients. You don't add any extra element. You don't make any changes to the subscripts. You make changes to the coefficients. And in more complex examples or more complex problems, you have to go back and forth between the reactants and products when you make changes in the coefficients. And therefore, it's at this stage, it's somewhat of a trial and error process, all right? So that's basically how that is done. Shall I cover this? Okay, let me just cover this and then I'll call it a day. Stoichiometric equivalence. Now, this underscores the importance of having the balance equation, because the balance equation, let me go back to the water example. The balance equation gives you the proportions of the different substances involved in this reaction. So one way of interpreting this equation is that 2 molecules of hydrogen will react with 1 molecule of oxygen to form 2 molecules of water. And that's very important because that will give you what we call the stoichiometric equivalence, or the mole ratios between the different substances. In fact, you can use the balance equation to establish the mole proportionalities between different elements. So based on the equation that we just saw on the previous slide, or previous 2 slides, you have 2 moles, you can establish the relationship between hydrogen and oxygen. 2 moles of hydrogen is equal to 1 mole of oxygen. You can do the same thing between hydrogen and water. And you can establish also a similar relationship between oxygen and water, right? And that's very important, as you're going to see later on when we do certain calculations, all right? So these are the conversion factors that would represent each of these relationships, right? So going to this first example here, 2 moles of hydrogen is equal to 1 mole of oxygen. You can represent it like this, or you can represent it like this, right? And in terms of problem solving, which one you're going to use is dependent on what kind of problem you're trying to solve. So if you want to solve for the moles of hydrogen and you're given the moles of oxygen, you would use this example right here. If you want to do the reverse, if you're given the moles of hydrogen and you want to find the moles of oxygen, you would use this example or this conversion factor right here. And of course, you can do similar problem solving with the other conversion factors as shown here, all right? So it's very important that you learn how to balance equations so that you can get the right mole ratio, which you're going to need for subsequent calculations. Okay, I think I'm going to stop here. The next topic we're going to discuss next class would be limiting reactants, and then we'll get onto a discussion of yields, percent yield, actual yield, and so on. All right, so Are there any questions? Any questions?
Okay, got it.
Let me see who came in late so I can have you down. So let me go here, go here. Come on. Oh, I should do this. Stop share. Okay, so is Arias Rios here? I don't see her name. Barber, Cannon. Oh, Barber's here. Cannon, is Cannon here? I don't see Cannon's name. Chang, is Chang here? DeGraff, Franklin, Han, Panic, Rouse, and Smith. Okay.
I'm here.
Oh, Smith is here. Sorry. Okay. Any questions concerning what I've just covered? Any general questions? Okay. Before I forget, I posted some information about the STEM Club. I don't know if you guys saw it. So if you're interested in joining the STEM Club, please do so. Just send me an email saying that you're interested, and that's all you need. And then you'll be contacted about the first meeting and other activities. I don't know if I talked to you guys about it before, but the STEM Club was formed last semester, just before the pandemic hit. Purpose of it is basically to introduce students to scientific fields, STEM fields, basically, so that you can broaden your horizon in terms of career options, all right? There's a lot of opportunity for attending workshops, for speakers, and one I'm particularly keen for students at CF to be engaged in, and that is the opportunity for scientific research in the form of internships. Very important. If I were you, I would jump on an opportunity like that because you get the experience of research in a lab with a university professor or somebody who is trained to supervise you, and you can publish your research, you can present your findings at conferences, and it would look good on your resume when you apply to, I don't know what you guys plan to do, graduate school, medical school, whatever. I would strongly recommend that you join this group because it will help you with all of that, all right? So if you're interested, just send me an email saying that you're interested, and we'll go from there, and then I'll notify you about when the next meeting is gonna be, and so on and so forth, all right? Okay, so if there are no more questions, that's pretty much it from me today. So have a good day, and I'll see you next class.
All right. Take care.
Take care.